Thank you for coming back. I'll then be building on the classical shadow formalism and start talking about a more challenging problem, which is so far we've been talking about how classical machines can see quantum systems through these classical shadow formalism. And what we would like to do next is to understand whether we can build on it, because now as classical machines can see many properties about quantum systems, we would like to know if that could help classical machines learn to solve some hard problems that arises in quantum physics. In particular, we would like to understand if they could yield potentially better solutions than non-machine learning algorithms. So that's going to be the topic of the talk now. But however, at the same time, I also prepare a part where at the last part, I would be talking about how quantum machines can learn even better than classical machines. And I would like to just, because we only have like 1 hour, a bit more. So I would like to know which portion do people wanted to listen to more. So then I could spend more time or like speeding up this part and then spend more time later or talking more about this part. So the two parts are using classical machines to solve quantum physics problem. And the second is whether quantum machines are more powerful. And for the first one, like just raise your hand if you like the first one more. Okay, thank you. And for the second one, okay. Seems like there's an, okay, then I'll be faster here. I think there are still interesting messages I would like to share here. Will also help us better understand how quantum machines can do better. So I'll still talk through this, but I'll be relatively faster. So, okay. In particular, to be more concrete, we'll be focusing on the problem of predicting ground states. And the problem here is the following. We have some high-dimensional vector x that describes some many-body Hamiltonian. And the goal of the classical machine is to be able to predict some representation of the ground state. So this representation could be the classical shadow representation or some other things. And in particular, these parameters, you can think of them as it specify what are the laser intensity on the quantum systems or some few-body interactions in the quantum system or the magnetic field that the quantum system is being placed in, and so on. And as we all know, this is an extremely hard problem. There have been a lot of computational hardness results that have been established. For example, if we focus on two-dimensional Hamiltonians with a spectral gap of 1, and the goal is to just predict one body observable in the ground state, then one can show the following proposition, which states that assuming NP-complete problems cannot be solved in randomized polynomial time, then no randomized classical algorithm can predict it efficiently in polynomial time. So essentially, there's a relation between solving this problem and solving NP-complete problems using randomized polynomial time algorithm. So yeah, and then one can essentially establish this, which states that this problem is very hard even if we focus on a two-dimensional system. And for three-dimensional systems, since that's a generalization of two dimension, that's also hard. So that's a computational hardness. So that just states that under reasonable complexity theoretic assumption, this is a very hard problem. And we would like to ask, so for this very hard problem, can classical machine learning algorithms do something useful about it? So in order for classical machine learning algorithms to work, one needs to feed it with some training data. And in this case, we assume that the training data are a bunch of examples telling the machine for this parameterized vector, this is the corresponding ground state, and for that vector, which corresponds to a different Hamiltonian, that's the corresponding ground state, and so on. So that's given by this training data shown here. And we're going to focus on the classical representation of the ground state to be given by classical shadow. So one could also imagine like one could replace that representation by, say, some tensor network representation or some other things. But in general, for 2D and 3D and higher dimension, we don't really know if there's some good efficient tensor network representation for them. So on the other hand, from the previous topic, we've already seen that classical shadow works for any state. So that gives a more broader like theoretical generality when we train it using classical shadow instead of using some more refined classical representation. So that's going to be what we're focusing on. So what the ML algorithm should do is learn from the training data. Now, given a new parameter corresponding to a new Hamiltonian that it has never seen before, people have never generated in the lab, we want the ML algorithm to be able to predict the ground state of that new Hamiltonian. So that's the task. So it's different from normal traditional algorithm, because traditional algorithm, there's no training data. It doesn't learn. It just tries to write down an algorithm that does this. But now the difference here in ML is that there's this additional training data that it can learn from and try to solve the problem faster. So now from the previous proposition, we've seen that in order for a classical algorithm to predict some ground state properties or some representation of ground state, it's already very hard under a very simple setting, like two-dimensional system, just predicting one body observable to some constant error, like 1/4. However, what we showed in this paper published last year in Science, provably efficient machine learning for quantum antibody problems, and also several other, after this work, there have been several other works that extend on it. So all of these results, the key, like on a high level, the key theorem states the following. It says that a classical ML algorithm can achieve an average prediction error of epsilon for any small constant epsilon. The epsilon can be like 1/10 or 1/20. And the classical ML algorithm will be able to predict accurately using only a logarithmic amount of training data in unloggen computational time, such that the algorithm works for any constant dimension, including 2D, 3D, any constant spectral gap, and any local observables. So essentially, yeah, together from proposition 1, it says that classical algorithm cannot do it. And here, this theorem essentially says that classical ML algorithms, when trained with data, will be able to solve the problem efficiently using a very small amount of training data and almost a linear computational time. So the key idea that happens here is that the classical ML algorithm, one can think of it as like a classical neural network that takes in some parameter describing the physical system and outputs some representation of the ground state to be doing the following. So think of x1, x2, x3, x4 as the existing points in the parameter space. It could be a very high dimensional parameter space. And for each of them, there's an associated classical representation of the ground state. And now what the ML algorithm would essentially do in proving this theorem is that it will, given a new x corresponding to a new Hamiltonian that has never been seen, it will essentially take all of these representations from the other points, try to synthesize them to generate a new representation for the new point x.
I have a question. Do you have to make assumptions on how the ground state looks like? Because even writing down an unknown ground state could take 2 to the n many steps, right?
That's a great.
I mean, if even writing it down at the end is more than you have available.
Yes. So recall like the representation we're using is this classical shadow representation, which can be written out efficiently on classical computer. So that's where we talk about, So we don't write down the full ground state as like an exponentially long wave vector. That's very intensive indeed. But using classical shadow, one can write it out efficiently. And
you're writing essentially down a code for that state in a way, right?
Yes, this classical representation of that much bigger state. Or you can think of it as like some kind of sketch of that bigger state. So that's why it becomes efficient using classical shadow. And so that's like the rough idea for the ML, like very rough idea for the ML algorithm. In order to achieve this log n sample complexity, the way to do it is to utilize structure in the problem. So essentially, the rigorous ML algorithm that achieves this scaling, one could think of it as kind of a rigorous version of a graph neural network. So you have a quantum system, it's like say a 2D system. You have all these parameters that talk about the few body interaction. What the neural network or what the machine learning algorithm would do is it will look at each local neighborhood. So you will look at each local neighborhood and then extract feature from them and then essentially combine them to make prediction. So that's how we achieve that. Right?
I wonder whether it's a little unfair because to train with the data, you need the ground state, which is the hardest part.
I agree. So there's definitely a difference. Like this result is trained with data, but normal algorithm, they're not trained with data. So, but I mean, they don't learn. So
So what that means is once you have the data or have access to the ground state, then you can compute the one body observable.
But that's only for the Hamiltonians that you have already got the data for. But the result here says that you can also predict the properties for new Hamiltonians that you have never created, you never get data for. So that's where what is. Yeah, within a set. Essentially, they're all it's a family of Hamiltonians, it's a smooth family, and then it's all spectrally gapped and so on.
So if you're going to use graph neural networks to learn local interactions, are you assuming that the global state is a product state?
No. The global state can be highly entangled. It's just, we can show that the functional form of going from this class of Hamiltonians to the corresponding ground state have a type of local property. But the state itself can be highly entangled. For example, one can imagine like toric code. So if you have a toric code, the ground state is highly entangled, it's not a product state, and yeah, one could apply these ML algorithms to toric code without problem.
Yeah. What are the restrictions on the distribution? Like, do you need IID sample ground states? And then are there restrictions on the Hamiltonians that you're actually using here?
Yeah, that's a good question. So we're considering some parameterization for a big class of Hamiltonians. So we can think of it as a vector, and then for each vector, there's an associated Hamiltonian to it. So and then the parameterization has to be sufficiently smooth. That's one part. And and furthermore, we are assuming that all of these Hamiltonians, they have a spectral gap. That is, the ground state and the first excited state has an energy gap that's a constant. They cannot kind of close, because when they close, there's so many ground state, and then the problem becomes very, very hard. So that's one part. So we're assuming that there's this family. And then for the training data, we're considering, so the result is that it can achieve a good average prediction error. So that is average over some distribution. And it can be any distribution over this family. But the training data has to be sampled from the same distribution. You cannot say sample from this distribution and then test it on a complete different one. Then the proof fails. So there's some kind of IID assumption that's happening here in order to make it work. Yeah.
So how do you ensure generalization that you sample from the same distribution, but the prediction can happen from any distribution? Like in normal ML algorithms, you make a lot more effort to introduce generalization into your neural network, right? How do you do that here?
Yeah, so here one can imagine this, right? The space is very big. Like, although I draw it as like a three-dimensional space, but in general, this is the dimension can be very large, can be linear in system size. So this whole bulk is exponentially large. So in a way, there's like exponentially different Hamiltonians in it. And here we're only training on a tiny bit of data. So now we only have a little bit of points. So the generalization happens in terms of like, you get a little bit of these points, and now you need to extrapolate out into the whole block. So that's where the generalization happens here. And the way we ensure that is, yeah, like there's these results in learning theory that talks about when you have some kind of function class of it, and then as long as some of its complexity is low, like for example, its Rademacher complexity of the function class is low, then you will be able to generalize. And here, the proof is essentially trying to do that. We wanted to show that the Rademacher complexity of the function class that will be induced by this physical problem is not very high. It's very low, and that's why it will generalize.
Okay.
Yeah.
So the problem is not similar to, like, I don't know if you've heard of when you use mixture of experts, the whole point is to learn all the different distributions that are coming from your language input. So you're saying that the same problem does not exist here, where even if you sample from one distribution, it's large enough that you can use that to generalize over multiple distributions in the prediction.
Are you talking about like out of distribution generalization, or?
Yeah, like.
So there's a setting. Okay, so in ML, there's also a different setting, which is you train on one distribution, and then when you're predicting in a complete different distribution. For example, you only train the ML model to read the Wikipedia page, but now you somehow wanted to make predictions about Shakespeare. So that's like a form of out-of-distribution generalization. And here we're not dealing with that. And also the theory there is very unclear. There has to be some kind of even underlying connection so that you can generalize. For example, you train it on classifying cats and dogs, and now you ask like, is this a human or is this a book? Like, it would not answer.
Yeah, it doesn't do well in active
Yeah, it doesn't do
context
well with
learning.
that. So here we're assuming more like you're sampling from some distribution. The distribution can span across a very big space. You only sample a little bit of points. And now we can guarantee that it would generalize to that big space.
Okay, but it will be the same distribution.
This will be the same distribution. Yes. Oh, sorry. Oh, I think I. Okay. Yeah. And so together, essentially, what these two results shows is that a polynomial time classical ML algorithm trained with data can predict much better than any polynomial time classical algorithm. And note that the data that was trained on can be very, very limited. And then it can generalize from the data to predict new Hamiltonians, new inputs that you have never seen before. Of course, like Lyndon stated, they're different because in the one hand, ML algorithms have these additional, not very much, but additional data that can help it do computation. And that's why it can be more powerful and more useful than non-machine learning algorithm that doesn't take in any data. And the central idea is that because now you have these data, you can rely on them, and you can just need to synthesize them in order to do computation. You don't have to compute everything from scratch. And that makes it much simpler. And furthermore, this philosophy can be explored from a purely complexity theory perspective. So in a paper with the Google people, we've essentially established a Venn diagram for the complexity classes that looks something like the one to the left. So we have BPP, which are problems that can be solved efficiently with classical algorithm. We have BQP, which are problems that can be solved efficiently with quantum computer. And now we have this other weird class, blue one, which are problems that can be solved efficiently with classical ML algorithms trained with data. And one can show that if you can get some training data, like polynomial size, now you can suddenly solve problems much more efficiently than BPP. So one might wonder, like, why does it go beyond BQP? So that's when you assume that maybe you get some data that is generated by things beyond BQP, which is a little bit shaky, but mathematically is just how it is. But if you assume that all your data are generated from quantum computation, then that blue circle will be inside BQP, but one can show that under reasonable conjecture, it will still be outside BPP. So that's kind of on a more complexity theoretic aspect, that's the power of using learning algorithm that learn from data.
In our use case, the data we use is only like quantum data, so it's going to be inside BQP still, right? And this.
So actually, in this, like recall that briefly mentioned, like this ground state problem, it can go beyond BQP because one can imagine these 2D spin glass model, and then if you want to find ground state, you actually need to solve an NP complete problem. So that's why actually even here it's already going beyond if we assume we can get these data. But if you assume that the data are always coming from quantum experiments, then it will be within it. Yeah.
Maybe real quickly go back to the CS side. So if you look at why quantum is hard, or it is beyond BPP, as you said. So there are results that the local, you can push it to 3 local, 2 local, it's still hard. And average prediction error is constant, that's still hard.
Yes.
Is there a version of the theorem that says it's still hard but the special gap is constant?
Yes.
Who proved that?
Yeah, so that's essentially related to this proposition that I mentioned here. In a way, this theorem was proven in our paper. But we are basing on some well-known results in complexity theory. Basically, there are these planar problem where one can show that it's like a planar constraint satisfaction problem where one can show that for those problems you can have a constant spectral gap, and yet it's like very hard. So we're basing on that in order to derive this proposition. And that's also why it's the assumption is a little bit different. Like it's not P not equal to NP, but like RP. So RP is a subclass of BPP. These are randomized. So the definition of RP is that when it's, I think it's one-sided, like when it's yes, like when the answer should be yes, it will always says yes. But when it's no, it will say no with like high probability. So that's RP. But BPP is like both sides, you can have some error, right? So RP is like a subclass of BPP. And yeah, so that's why it's a little bit different, because the situation is a little bit different. But
can this be turned into a QMA continuous?
yeah, no. So that's why this is also MP. So I think when the spectral gap is constant, then there's no like
there's no
QMA hard. Yeah.
So that's why it's a little bit shaky.
Yeah.
Whether it goes out of BPP.
Yeah. But I think people believe that NP is incomparable with BQP, so it could.
What's the size of the gap in the Kitaev construction?
That's an inverse polynomial. Yes. Yeah, but essentially together, the proposition 1 and theorem 1 says that in a physically relevant problem of predicting ground states, an ML algorithm, a classical ML algorithm, can be more powerful than classical algorithms. But of course, the power is not coming from neural network or ML, but coming from the fact that it can learn from data and generalize from data. Here are some numerical experiments where we consider training an ML model for predicting ground state properties of a 2D random Heisenberg model. Here, for the system size we consider this 5 by 5 to 9 by 5. One could also use like a snake-shaped DMRG to solve the ground state. But then DMRG algorithms using snake shape, it would have a computational complexity that grows exponentially in the side of the like a square root of the system size. So itself is still a super polynomial time algorithm. On the other hand, this ML algorithm is almost linear time, and we can see that the prediction from an ML algorithm is visually indistinguishable from DMRG. So here what we're predicting is we're predicting the two-point correlation function in the ground state of these 2D random Heisenberg model. One could also prove a theorem for not predicting ground state, but for classifying quantum phases of matter. So here the task is we're given some classical representation of the ground state, and we would like to predict if it's in a trivial phase, in a symmetry broken phase, or topological phase, which is a problem that physicists are very interested in. And essentially, using similar tools, which are also built on classical shuttle, we prove a theorem that says as long as there exists a nonlinear function based on few body reduced density matrices for classifying the phase, the ML algorithm can efficiently classify these phases. Particularly, this assumption is believed to be hold for any constantly gapped quantum system. And this is also, again, a numerical experiment for this particular task. So here we have a phase diagram that looks like figure B. So that phase diagram was developed through a big chunk of physical studies, and people discovered that there's the trivial phase there, and there's this triangular symmetry broken phase on the top, and then there's the topological phase on the right. However, one can imagine maybe we don't know that. We don't know that phase diagram exists because we're exploring a new kinds of quantum matter. And in that case, what one could do is one can just take a bunch of states from that parameter space. So like in the figure C and D, we're considering this line and also this line. And we just take a bunch of states there, and then we feed it into an unsupervised machine learning model based on an algorithm that we use to prove that theorem. And now, essentially, when we apply it, what the ML algorithm would do is it would just find some low-dimensional representation for these states, and we can look at the low-dimensional representation it finds, and we see that, say, in figure C, when we focus on this line, which has two different phases, the ML algorithm correctly identifies that there's two different phases, and then for delta equal to 3.0, where there's three different phases, the ML algorithms can correctly identify there are three different phases. So one can see that it works well, and furthermore, in a supervised case, one can establish a rigorous theorem that says it will work well, because these problems are not that hard, so classical machines can just solve them. So together, that provides some of the initial answers to the question of what can classical machines learn, and can classical machines learning algorithms perform better than non-machine learning algorithms. And what we have seen so far is that there are various quantum problems, like predicting ground states in gap system, and also like classifying quantum phases of matter, which are all intrinsically quantum problem, but yet you can use classical ML algorithm to solve them efficiently and rigorously. So given all these results, a very natural question is, then what are some things left for quantum machines to do? There are some kind of problems where we can say, using quantum machines, it will learn exponentially faster, or it will predict much more accurately than classical machines. So that's going to be the topic of my next part. Again, I'll be focusing on learning in the quantum universe, since our world is quantum, and then intuitively feel like quantum machines could be better. But because of all these results that I mentioned in the first part, a lot of quantum problems, you can already do them provably efficiently with classical. So that leaves open whether quantum machines are actually needed and what kind of advantage can we actually gain in learning. So that's going to be the part. And that's going to be what I'm going to focus on for the next 50 minutes. In particular in,
I'm sorry, you can solve these things efficiently classically with quantum training data, right?
in a way, yes. So what I was trying to distinguish is between whether you need like a quantum machine learning algorithm, like a algorithm that can, like a quantum machine that can actually learn. But apparently here you don't. So you just take some data, train it classically, and then you can solve it. But yes, indeed there is some data. So like maybe that data can be generated by a quantum computer, but that's not a quantum computer that learns. It's just a generation thing. So we're wondering more about the learning aspect rather than just a pure computational aspect. So yes. Okay. So I'm going to switch the language a little bit because I want it to be a little bit broader. So we'll be talking about classical agent and quantum agent. But you can think of it as just classical machine and quantum machine. But the classical agent can be human. And I don't want to keep calling human classical machine. It's a little bit weird. And yeah, so what we define as classical agent goes back to the starting point on how I define learning. So we say a classical agent is a learning agent that can receive, process, and store classical information. So it can receive classical information by doing measurements, by doing experiments in the real world. It gathers all these data. That's what scientists do all the time. And then it can process these data with classical computation, like on classical computer or with our brain. And then it can be stored in the classical memory. On the other hand, as quantum technologies start to develop, one can imagine there's these quantum learning agents. So the quantum learning agent receive, process, and store quantum information. So for example, in the future, there could be a quantum learning agent that have quantum sensor that can take quantum information from the world. And then what it can do is it can store that quantum information in a quantum memory instead of a classical memory. And it can perform quantum computation to process these quantum information, to perform learning, and to perform prediction. So that's the distinction between quantum agent and classical agent. And now given this dichotomy between two sets of agents,
When you talk about quantum memory, do you mean like short quantum memory, or do you actually mean a long-lasting quantum memory?
Sorry, what?
Do you mean a like short-lasting quantum memory, or do you actually mean a long-lasting quantum memory?
Oh, yeah, I meant it's a quantum memory of polynomial-sized qubits, and it just stayed there. So like a fault tolerant style. But actually, a lot of the results that I'm going to talk about, it can also be a bit short range. Like you just need to exist a little bit of time, and then it can already have some advantage. But in the more futuristic sense, we're assuming this is like fault tolerant quantum memory, fault tolerant quantum computation, some very robust quantum sensor, and then they all can talk to each other. So that's very futuristic. Right now, we're at a stage where there's some development on quantum Okay, so I guess the first development that people are doing is to first get a good long-lasting quantum memory. And then we can talk about fault tolerant quantum computation. And then quantum sensor people are doing their own thing on the side. And there's also people working on transduction, which can connect these things. But all of these are different fronts of the scientific frontier. And so this is more futuristic, but as I would talk, there are actually experiments that one can already done now that illustrate the power of quantum learning agent. But when I was talking these more abstractly, one should think of it as a futuristic entity, which is these quantum learning agents. Okay. So now given these dichotomy, one of the very important question is understand what are the advantages of having a quantum agent over a classical agent. And understanding this question is not just important for the field of quantum machine learning, but it's also important to understand this because it will tell us whether in the future quantum technology can really change our ability or improve our ability to learn about the physical world. So that's the kind of the motivating question. It's very broad. And to make progress, we're going to take small step at a time. In particular, I'm going to restrict to a very basic problem, which is about learning a state. So it kind of goes back to the beginning. So we care about a lot of things in the world. We wanted to understand how black holes are actually doing so that we can resolve this mystery of quantum mechanics and general relativity. But for now, I'm going to focus on learning states. And so there's similar to before, there's some unqubit state that we will care about. We would like to be able to learn it. We would like to be able to make predictions about it. And the classical agent, what it can do is it can perform measurements on rho. So in each experiment, it performs some POVM, kind of like what I talked about. Maybe it rotates the systems that it evolve and then measure. So it gets classical data, it stores all this classical data in classical memory, process them, and then make prediction. On the other hand, one could also imagine a quantum agent which can obtain and store these quantum state rho coherently from each experiment, put it in its quantum memory. It can put many of it in its quantum memory, and then do a quantum computation on all of them. So that's the dichotomy between quantum agent and classical agent for this very basic task of learning about a state. But I would like to expose it even further. So these are like a flowchart of what classical agents can do. So we assume that there is a physical source that would generate a single sample of a state rho at a time. So what the classical agent would do is it would just look at the state under some basis, essentially performing a measurement to obtain some classical data. It stored that classical data in its own classical memory. It can then process that classical data to think about what kind of next experiment should it do. Should it measure the same thing, or should it measure a different thing, etc. And then after deciding what to do next, the classical agent will perform the measurement, obtain classical data, store the classical data, process it, and then this just keep repeating. So it performs, say, t times p experiments, and now it would have a classical memory full of data coming from these quantum experiments. What it would then do is it would then, say, for example, process it once again, process all the data, and then can start making prediction about this physical system rho. Like it can start predicting properties about it. It can start answering questions, like these ground state questions that we talked about earlier, or the phases of matter questions, and etc. So that's a situation, like a flowchart for what classical agent can do. On the other hand, the quantum learning agent, as I discussed, it receives, processes, and stores quantum information. So again, still have a physical source that could generate a state rho at a time. And what it would then do is it would then use this quantum sensor to obtain that quantum state and just put it in its quantum memory. So now in its quantum memory, it would have one copy of the state. And then because it didn't do anything, so it essentially captures everything. So at the second experiment, it just do that again. It uses quantum sensor, capture the quantum information, put it in the quantum memory, and then keep repeating it again for, say, t experiments. And now after that, there would be a quantum memory full of these quantum information. It would then process it using quantum computation and then make prediction about the quantum system, about the physical system rho. So that's also, again, like a flowchart of what quantum agents could do. So now what we would like to understand is, now hopefully this is a good abstract framework for understanding what they could both do. Oh.
Does the first step of this process on the previous page constitute a copy or a clone? For the quantum side?
Oh, the quantum.
Does this constitute a copy or a clone of that quantum state?
Yeah, it essentially captures a sample of the quantum state. So you should think of the rho as like because it's a mixed state, so it could be a distribution over a pure state. So every time when you capture one, you capture kind of one instance of the pure state. And yes, it just stores that pure state in its quantum memory. Yeah. So now the question is, okay, so now we have these two settings. It can see, it's conceivable that these quantum agent, because it can do more, it can entangle these information. It doesn't necessarily have to decohere, like measure things to get classical data. One would like to understand if these quantum agents are actually more powerful. So one of the results that was proven was focusing on the task of predicting Pauli observables. So in this setting, the agent, the classical or quantum agent, go through these processes to learn about this state role. And now after learning, someone would come by and start asking these agents some questions. And the questions are always of the form, here's a Pauli observable, which is just a tensor product of the Pauli matrices, Ix, Y, Z. Please predict the expectation value of these Pauli observables. So there's a few mathematical property about these Pauli observable. First of all, if it consists of only X, Y, Z, then it's very high weight. It acts on the entire n-qubit system, so it's not a local observable. And furthermore, they are high rank, so their Frobenius norm is actually very large. And hence, these Pauli observables are not amenable to the classical shuttle framework that we talked about earlier. Those only works for bounded Frobenius norm and also for observables that act on few qubit. And this is neither of them. But maybe there are some other protocol. Maybe there are some other classical shuttle or classical agent protocol that can predict them. But essentially, the following theorem says that this is not possible. So a classical agent would require an exponential number of experiments just to even predict one adversarially chosen observable. So think of the setting again. So it's the classical agent go through these experiments, learn a model, and now someone comes by. So that person can just adversarially choose some observable, P, and then the classical agent will fail if it doesn't do exponential number of experiments. On the other hand, one could also prove that a quantum agent actually only requires a linear number of experiments in order to predict all 4 to the n observables. So this is really all 4 to the n. That is, someone come by can just keep asking these quantum agent questions, exhausting through all these exponential many observables, and the quantum agent can just correctly answer all of them. And furthermore, this exponential separation is already present when the state role that we're looking at is very classical. So one might say, oh, maybe it's because the state role has some crazy entanglement in it, and that's why quantum agent can do better. I mean, that's a natural case when it could do better. But the separation is already present when the state role has no entanglement in it. It can just be a probability distribution over product states. And yet one can still prove a theorem like this. And the basic idea underlying the theorem is that classical agent, because it can only perform measurements to get classical data, it will be subject to uncertainty principle. So the thing about these Pauli observable is that they're highly incompatible to one another. So these X, Y, Z, they don't commute. They anti-commute. And that uncertainty principle of these Pauli observable significantly hinders their ability. So if they perform some experiments to get information about some Pauli observable, they will not be able to get information about a large number of other Pauli. So in order to get information, they really need to perform a large number of experiments. So that just kind of comes from Heisenberg's uncertainty principle. But what's strange and surprising is that that doesn't apply to quantum agent. When the quantum agent can take all these data and store them in a memory and then perform an entangled measurement or like a quantum computation on top of it, it can somehow circumvent uncertainty principle. And then it can just predict a bunch of observables simultaneously. So that's kind of on a more intuitive level, that's the idea of this theorem. And that's why there's a big advantage in it.
Question. You mentioned this also works for classical probability distribution. Then what is the analogy of uncertainty principle?
Yeah, so it's actually a classical distribution over product states. So it cannot be just 0, 1 basis state. And there's no uncertainty principle.
What is the size of the output of the O of n experiments?
Good question. So actually, the quantum agent, after doing the experiments, it just needs to store like a quantum model of size roughly order n square qubits. So it has this weird quantum model that it stores in its quantum memory, and now when you ask questions to it, it can do some very efficient computation, and it will produce the answer correctly. So in a way, the output of that quantum agent, which can only be read by a quantum agent, is this unsquared
So it's
qubits.
huge.
Sorry?
It's large, right?
Oh, unsquared is not that large, right? It's not exponential. That's what I was.
Oh, okay, okay.
Yeah. It's just unsquared.
So how frequent are these adversarial chosen examples? So if a random poly is it adversarial, or is it like a very small set of polys that are adversarial? Like,
Yeah, that's also a great question. So it's well known that if you just choose Pauli uniformly from that set, then almost always you're going to see a value very close to 0. So that's true. So in a way, but at the same time, you're not going to choose uniformly over P. Like usually there's some subset that you care about, and yeah, like maybe it's a big polynomial. And there's like a version of it, which is suppose you consider some subset of P, like a polynomial size subset, then the classical agent will have to be omega of that polynomial, but then the quantum agent is actually just logarithmic. So there's still an exponential separation, but not as like 2 to the n versus n, but like polynomial versus log n. So the separation changes, but for here, we focus on the full case.
So given so many of them are close to 0, then accuracy matters, right?
Yeah, so here we're only focusing on, all these statements is all focusing on constant error. So like just predicting up to like 0.2, for example.
Is it constant accuracy a meaningful thing?
Yeah. So even for constant accuracy, it's already very hard for classical.
But you said earlier that for most of, if you choose it randomly, then they're all very close to 0.
Yeah, so one shouldn't choose it randomly. Like this Pauli set is kind of large, and then you just choose it randomly, it will just be 0. So one just shouldn't do that.
So it is very much concentrated on some polys. You just don't know.
Yes. But usually that's like, yeah. But usually for some physical system rho, there will be a natural set of Pauli that you care about. For example, in chemical systems, there's going to be a bunch of these long string Pauli P that corresponds to, like, say, the Jorgen-Wigner transform of local reduced, like, fermionic operator. Then that will be like a polynomial size set.
But then they're local in some sense, right?
Yes.
Local.
Yes.
So yeah, I'm just wondering, so if it is truly local, then you can do classical shadow.
Yes, but fermionic local, it becomes strange. And basically, there's a recent result that was not published. It's also not done by me, but there's a result that says for fermionic operator, if you just do if you use a classical agent, then it will always have a polynomial scaling. But if you use a quantum agent, it's logarithmic scaling. So that's what I was.
They have a paper on fermionic local.
Yeah, they have Ryan has a paper, but that scaling is actually polynomial. It's faster than just going through individually, but it's still like a polynomial.
So then, in that case, the gap reduces to a polynomial.
Yes, so it becomes a polynomial here, and then a logarithm log n here. Yes. Okay, so if there's no more question, now I would like to talk about how one establishes this theorem, which uses some new ideas from learning theory. So in particular, I'll be focusing on proving the lower bound for classical agents. And the key idea is to consider the following graphical representation for how the memory state of the classical agent transition. So at the starting point, let's say the classical agent's memory is represented by a root node R. Every experiment, when it performs certain things, it will see the outcome, and that outcome would cause its memory to change. So it might jump based on, say, outcome 1. It might jump to a point here, and it might jump to another point if it's outcome 2, etc. And then just keep going. In general, this is a very weird graph. It doesn't have to be a tree that's shown here. But the key idea there is that when you have two nodes, A and B, such that they both go to C, then when you're at that point C, like the classical agent is at that point C, then it will not know if it comes from A or B, so it means some information is lost. And essentially, one can show that for the optimal classical agent that minimizes the number of experiments, it shouldn't forget about things. So essentially, one can show that this kind of graph shouldn't exist, and one can always focus on having this tree representation for considering how the memory state of classical agent changes. So it will start from some root node. Based on the experimental outcome, it might move to one point of one of its child node, and then continue. And this tree will be exponentially growing. So if one conducts t experiments, then this tree will have a depth of t and a number of leaf nodes that scales exponentially in t. So that's the picture one should have. In particular, for if the underlying state is different, so you can imagine like there's two different physical reality, then the distribution that walks the tree will be different. So if it's row A, then it might have a walk that is biased towards these two final nodes. But then on row B, maybe it's biased towards this node and this node. So the distribution is different. And the key idea here is that if the classical agent is able to learn about certain things, like learn certain aspects of the physical reality, then it should be able to distinguish some sets of physical reality, which also means that the leaf node distribution should be sufficiently distinct between different physical reality that it tried to distinguish. And furthermore, there's some facts. As the number of experiments increases, the tree gets deeper. And as the tree gets deeper, the distinction in the distribution over the leaf nodes would also widen. So the TV distance grow and makes it even easier to distinguish, which are all intuitive because more experiments means it can learn more, meaning that it can distinguish better. So now what we would do is we would try to reduce this learning and predicting task into some distinguishing task. Particularly here, we're going to focus on a many versus one distinguishing task. So recall that the prediction task is we would like to be able to estimate trace of p row to some constant error for some Pauli observable p. And then we wanted to say that if the classical agent can achieve that prediction task, then it can achieve some distinguishing task. And a distinguishing task that we look at is something like the following. Essentially, there's going to be a null hypothesis where the state row is just a maximally mixed state. And then there's going to be an alternative hypothesis, which is some alternative reality where the underlying state is not a maximally mixed state, but a state of the following form. It's I plus some Pauli divided by 2 to the n. So these states have the following structure, which is they can actually be written as a classical probability distribution over product state. And furthermore, when you try to estimate trace of p row onto these states, so if you try to estimate trace of p maximally mixed state, then this is just going to be 0 for all Pauli. But if you do that for one of these alternatives, it's going to have some value at a specific Pauli p, so in particular this PA. One could also consider changing the different Pauli, so we have PA, PB, and so on. So that's all the alternatives. And now recall so essentially one could see like if the classical agent can achieve the prediction task, then it will be able to distinguish between the null hypothesis and these alternatives because of the fact that I just mentioned. And what that means is that the leaf nodes distribution in the null hypothesis will be sufficiently distinct from the average of the leaf node distribution for the alternatives. So that's essentially what we're going to characterize.
Sorry, I just got confused. Do you mean that this can just predict that it's either null or not null, or can it just distinguish which one of the alternatives it is?
Sorry?
So is it going to just like distinguish that it's null or not null, or can it just distinguish which one of the alternatives it is? The classical.
You mean if it's 0 or not 0?
Yeah.
Yeah.
Is it just binary? Is it just like null hypothesis or not?
Yeah, but I mean, it's always going to be, the prediction task always has errors in it. So it's more like it will see that, oh, it's like close to 0 versus it's not close to 0. Then that's like a reduction where if you have an algorithm to do that, then you can distinguish between null and alternative. In particular, we're going to focus on a specific situation because I mentioned earlier, like even just predicting one adversarially chosen is hard. So what would happen here is we will set it up so that the underlying state is either, say, I over 2 to the n, or one of these two. And then for some random p. And then we would just reveal to the classical learning agent after it has done all the experiments, say, please predict the expectation value with PA. And then you just look at what it says. If it's close to 0, then that should be null. And then if it's far from 0, that should be alternative. So that's the situation. And then what we then do is now we have reduced it to distinguishing task. And in order to do distinguishing task, in order for it to distinguish well, the probability distribution has to be sufficiently distinct. So what we would then do is we would then try to understand the total variation distance. So that's the next thing we need to get a handle on. Essentially, what we will do is we will upper bound the total variation distance with a function of the number of experiments. So as the number of experiments grows, the TV will start to grow, but it will grow very, very slowly. It will grow exponentially slow, such that you need an exponential number of experiments in order for the distinguishing task to work. So that's like the overall structure of the proof. And if one could do that, if one can prove that the TV must grow like very slowly, then one will be able to establish this exponential lower bound for the classical agent. And the proof of this TV is actually very simple, so I wanted to go through the detail. So the one that we wrote in the paper is already very simple, but I was actually talking to Ron DeWolf just a few weeks ago, and he found a few places where one could speed up the proof, and the proof can be much shorter. So I wanted to just showcase that very short proof that says the TV will grow very slowly with the number of experiments here. So if there's no more questions, then I'll.
Can I ask a question?
Yeah.
So what you really show here is that if you want to develop a genetic procedure on the TV, yeah, it's very hard. But for this question to make sense, that is, you only tested this to a constant procedure, you need to focus on rows which has this hidden quality that has a high weight, right? Which is after almost the same question as Scott Harrison. It has been asked on Monday, but also many other talks recently.
Yeah.
It's literally the same question.
Yeah, in a way, that's very much related.
Right. So if you restrict to such kind of states, is it clear that how hard this is for the classical thing to do?
Oh, you mean if you have a state where...
Restrict to state
Yes.
with a hidden quality that has constant weight.
Oh, that's actually the state that was generated here. Yeah, let me just say, like, if it's I plus PA divided by 2 to the n, then trace of P, this is equal to delta, whether P equals to PA or not.
What's the quantum state?
Oh, this is the quantum state. Oh, P is a Pauli. Oh, P is the property we would like to predict. So given some Pauli P in I, X, Y, Z to the n, excluding the identity, then it would have this relationship. So it's very pointy, actually. So.
Right, but the problem is not like it is hard to come up with something that is pointy, because you come up with U and you never, it's very pointy, the identity. So the problem is you know this PA. Is there like you maybe we can discuss that.
Okay, sounds good. But yeah, but in general, bounding this total variation distance can be quite tricky because there's some weird tree structure on it, and then we would like to understand like how does this, and this is a distribution over exponentially many different things, and we would like to understand how the TV grows with respect to the number of experiments In general, it's quite, yeah, I mean, a priori it's hard, but actually in our paper, we have developed several tools that allows one to deal with this situation quite easily. And in particular for this case, the proof is very, very short. So let me just try to sketch the whole proof. So what I'm writing down here is we consider, like here, there's this PA. We consider PA to be randomly chosen. And then this P0 is just a probability distribution for the null hypothesis. And this P plus minus PA is the leaf distribution for one of these two alternatives. So either I plus or I minus. So that's why there's a plus and minus. And essentially, our claim is that no matter what the classical agent, like what kind of experiments the classical agent do, no matter what it does, and then after doing it, it would be at some memory state, the distribution between P0 for the null hypothesis and the average of the two alternatives, the distance between them would on average be very small. And yeah, but in order to establish the distinguishing task, we also have the fact that it must be greater than or equal to some constant in order for it to correctly distinguish it. And then what we are essentially going to do is we will then go through some derivation and then show that the TV is actually bounded by something like t over 2 to the n plus 1. And as a result, t is the number of experiments. And as a result, we see that t must be greater than some exponential number. And so how do we bound it? Because this seems like some crazy object over this big tree. So one of the first things we will be looking at is we will consider an equivalent format for writing out total variation distance. So total variation distance is actually equal to, so these are summing over all the leaves. Is this. Essentially, the thing we're doing here is instead of looking at their absolute value difference, which are kind of object that's kind of hard to bound, we look at kind of like a hinge loss style. So like there's max 0, 1 minus their likelihood times P0 of L. So in particular, we're going to be studying their likelihood and then plug it back in. So is this identity clear? Essentially, like in normal TV, it's just the 1/2 of the sum of the absolute difference, but you can focus on only the portion where one is bigger than the other. Like if P0 is bigger than P plus minus P part, and then consider this maxing. And then one can remove the 1/2. So this identity holds. And then the key idea is to try to bound this object. And bounding this is actually very, very, very easy. It's going to use some very elementary inequalities. So the first one, this is the one that people learn from maybe middle school or elementary school. So AMGM inequality, and then so that's the first step. There's not many steps. And just to recall, like I haven't written it down, but the probability of a leaf nodes is a product of a probability for going through every edge. Particular. P rho of L. So if the underlying state is rho, then the probability that we will land at the leaf node would be equal to the product for each experiment. So there's T experiments, and every experiment there's a POVM measurement, but there's a reduction that one could show that for these classical agents to do their best job, they should always consider rank 1 POVM, which is a POVM where all the elements are rank 1. That has the best distinguishing power. So a rank 1 POVM, when you measure it, the probability that it would come out would look something like this. So the state rho is the thing we care about, and then this phi LT is like the measurement. So in the case of projective measurement, these phi LT just corresponds to exponential number of like orthogonal state. And then all of these W are just 1. But one could generalize it to POVM, and then there will be some weight, and then there will be some non-orthogonal collection of like pure states. So we have that. Hopefully that's clear. And then we can just plug this into here using the fact that this rho in this 0 case is just a maximally mixed state, so it's very simple. And then for one of the two alternatives, it's also pretty simple. And together, what we would, oh, that's so hard to push. What we would get is this geometric mean will be equal to the square root of a product the W part just canceled out because both are degree 2. And the 1 minus squared just come from one side is I plus, and then it's another side is I minus. So together, we just get this. And then one can, again, use a elementary inequality to bound it by 1 minus. This, just remove the square root because this number inside is between 0 and 1. And hence this is 1 minus the sum 1 to t phi L t p phi L t squared. So the likelihood that we're the likelihood that we're looking at here can be 1 minus the likelihood. The likelihood itself can be lower bounded by 1 minus this guy. So together, I'm having so much trouble with that. So together what we have is the TV can be upper bounded. The TV can be upper bounded by the average of a Pauli sum over leaf nodes P0 of L times, if we plug this lower bound into that max function, it would only leave this term left, sum over t from 1 to capital T, phi L t p phi L t squared. And it's almost done. Basically, we just need to realize that when we take an expectation value of a Pauli operator with respect to any state phi squared, this is always equal to 1 over 2 to the n plus 1. And this can be seen just by using the fact that Pauli operator form an orthogonal basis for Hermitian operator, and yeah, and also phi they have a norm 1. So together with some expectation value here, they will show this. So yeah, so now if we plug everything back in, this is just equal to t over 2 to the n plus 1. And that's the entire proof. It's very, very straightforward. So that's the way one could analyze TV. And the analysis is particularly simple for this Pauli observable case. But for some of the other problems I'm going to talk about, it can get more complicated. But that's roughly the idea. The idea is that, so from the proof, one could see that originally we are dealing with this tree. It's very complicated. We need to look at all the leaves. But what we do is we just look at one leaf, then we look at the path that come from a leaf, and then we just try to analyze the difference, the likelihood difference for that single path. And then just using very simple like AMGM plus some trivial inequality, we can see that the likelihood for that one path can be understood by essentially a likelihood for the individual edges. And for each of the individual edges, there's this notion here, which one can understood this equality as some kind of an uncertainty principle. It says that, so suppose that the Pauli operator, say we consider some collection, such that they're all commuting. Then one can look at the commuting basis, like the simultaneous diagonalization basis, and one can pick a state, phi, such that the number is all large. So the expectation value should be some large number. However, what happens for Pauli is that they're highly incompatible to one another. So no matter what kind of pure state you choose, phi, their squared, like their magnitude squared on average must be very small. So like the information is kind of spread out. That's also why when you randomly sample Pauli, it's usually very small. But that's also, one can think of it as a characterization of the incompatibleness of these Pauli operator, which give rise to their uncertainty, the uncertainty principle aspect of it. And basically by looking at every edges, so here this t from 1 to t, they're just talking about each edge at a time. That kind of the information you gain from each edge is very small. So together with t experiments, the total information is still very small if t is not exponential. And that's essentially the idea. So we're looking at each path and then try to understand the kind of for each edge, how much does it contribute. But more generally, the problem of understanding TV can be quite difficult. So some of the proofs that we're using to show that there's an exponential advantage requires a more complicated analysis. Like we need to really do like a random walk on the tree and then try to do some martingale concentration in order to show that the TV is small. Like try to essentially look at the likelihood martingale and then understand that, oh, that martingale concentrate and then it's like very close to 1, etc. But here, this is very simple. But it also gives a nice exponential separation. So now that's how one bounds TV, and one established the theorem that says classical agent requires exponential experiments, but quantum agent only needs linear. More generally, one can think about, oh, if there's like a collection of some observables, so 1 till m, what's the scaling there? Particularly in that case, we have the following theorem, which says a classical agent would require the minimum of m versus 2 to the n experiments in order to predict m observables.
Could you say again, what's the key that the quantum?
Yeah, so from this derivation, it seems like, oh, wow, these Paulis are very incompatible. The idea there is that when things are incompatible in the original space, when you consider a tensor product space, they can start become compatible. So one example is for Pauli is this. So usually when you have two Paulis, P and Q, they don't necessarily commute. But when you consider their tensor product with themselves, then any Pauli term, they commute. So in a way, like when you work in two copies, like a double space, then suddenly you can estimate properties about all of them simultaneously. But now you're estimating some different property. So one way to think about it is like, if you consider P tensor P, apply onto rho tensor rho, then this is just equal to trace of P rho squared, which means that one can simultaneously measure the magnitude of all of these different Pauli operator to a small error. However, there's still a sign that's missing. So in order to get the sign, one needs to do a more complicated quantum algorithm. But I would say intuitively, the key idea is that when you go to a bigger, like when you double the system and when you allow multiple copies of your data to be put into a quantum memory and then jointly measure all of them, you can get information that you will not be able to get in a single copy situation.
So can you sketch how the quantum learning algorithm is like?
Yeah. So the quantum learning algorithm has two parts. There's a part where it just, for every pair of experiments, it would store a copy, and then it performs an entangled measurement on them, so that then it would get some classical data, which allows it to predict the magnitude. So there's two parts there. First part is predicting their magnitude. And this can be done by essentially storing two copies in memory. Think of them as like an n-qubit system. And essentially what one does is for every pair of qubits, one measure in the Bell basis. And then that gives rise to a classical data, which can then be processed to predict this. And then there's a second part, which is predicting the sign. And for this part, the algorithm is more complicated, and it has to be, we use this as a form of protection from the first part. So the idea is we store multiple copies of this rho in a quantum memory. And then whenever we wanted to estimate the sign, we will perform a coherent majority vote. So there's multiple copies of rho. When we wanted to estimate the sign, we given a P, we go through it, we do like a coherent measurement. So we store the measurement outcome in one additional ancilla qubit, but we don't really look at them. And then we perform a coherent majority vote to get the majority of these ancilla qubits in a new qubit. And then we measure this qubit only. And after measuring that, we uncompute everything we've done. So that's kind of the idea that was used there. It's like a coherent majority vote plus coherent measurement. But then there's a problem, which is when you do a measurement here, you might have destroyed all these information. So now the quantum agent can no longer predict. Like it might be able to predict one Pauli, but then its memory got destroyed, and then it cannot predict anything more. So it has to essentially use the first part to protect it. Then the protection is the following. If the magnitude is very close to 0, then you don't do the second part. You just output 0, because you know that the number is close to 0. But if the magnitude is far away from 0, then you go to the second part and do this coherent majority vote. And because now when this magnitude is far away from 0, this coherent majority vote will give rise to the sign with very high probability. One can then utilize this technique called gentle measurement lemma or quantum union bound in order to show that the quantum memory will actually get undisturbed. So it would just preserve, and then one can just keep using it to predict all Pauli operator. So that's like an overall sketch of for the quantum agent to avoid uncertainty principle in this Pauli operator. Okay. Yeah, I guess it's almost time, but let me just say a few words. So in addition to estimating incompatible observable, one can also prove an exponential quantum advantage for performing, say, quantum principal component analysis. So this part is a little bit, there's some interesting backstory in it. So this PCA algorithm was already, quantum PCA algorithm was known like 10 years ago. So Seth Lloyd, Masuma Sani, and Patrick Rabentras has this nice paper. And some aspect of it is dequantized. So basically, if you assume that you have access to a sample and query model of a state rho, then you will be able to do quantum PCA classically. However, it's not in this quantum setting, it's not entirely clear how one would get this sample and query access. And essentially what we prove is that if you just can perform measurements on rho, then classical agent would actually require exponential time. But quantum agent only needs polynomial. So in general, there's still an exponential advantage in quantum PCA, although in some aspects of it, it's been dequantized by Yi-Wen Tan. And there are other exponential quantum advantages, such as uncovering symmetry in dynamics. So there's some dynamics that's happening, you wanted to know if it has time reversal symmetry. We can also prove that for this problem, classical agent requires an exponential number of experiments, but quantum agent only requires polynomial. And if you wanted to learn some effective model to describe some polynomial time quantum process, there's also an exponential separation between them. And furthermore, we've done experiments on Google's Sycamore processor to showcase that some of these advantages that I talked about can already be utilized in a NISQ regime. So these advantages of using additional quantum memory to perform entangled measurements and so on, one can already see that even if there's quite a significant amount of noise in the current processor people have. So these are just some details of the experiment. But together, it paints the following picture, is that classical machines, they're very powerful, they've already done a lot. But if one have classical learning machines, one can solve problems that are hard to solve classically by utilizing these training data, such as in predicting ground state. And then furthermore, when one has in the future these quantum learning machines, they can do things even further. And all of these separation, one can essentially prove it rigorously. The first one is conditional on some complexity theory conjecture, and the second one is unconditional, as we have shown, through the proof. So just to conclude, there has been a lot of progress in understanding how we can learn in the quantum universe. However, most of it has been focusing on some very fundamental tasks. We have some good understanding. Of course, not everything is known. I think there's still a lot more to push on understanding how classical machines can learn about quantum systems. We're still working on it. But on the other hand, there's also going further, how can we design rigorous ML algorithm for higher level tasks? Can we have an algorithm that can learn quantum algorithm? Can it learn to discover new physical phenomenon? All of these are very high level, and it's not entirely clear how to make progress. But more concretely, classically, we have neural network, which can do a lot of great things. But quantumly, we don't have an analog. People have been looking at quantum neural network, but they're untrainable in all kinds of ways. So how can we really design the right definition of quantum neural network? That's a very concrete thing that's missing. And it has been missing for a long time. So I think that's an important question. But finally, I wanted to end on a very long-term ambitions. I think some of the big motivating questions of this field is, for example, can we develop some algorithmic theory to help us accelerate and automate science and discover new physical phenomena? And can we build a quantum machine that is able to learn and discover new facets of our universe beyond humans and classical machines combined? These are very big questions. We're trying to make progress. I think we're in the right direction, but it's still very far reach. But I think maybe after 50 years or 100 years, we would have some understanding of this. And that's it for my tutorial. Thank you so much.